Okay. So our first step, NO2 plus NO2 makes NO plus NO3. Our second step, plus CO2. And this is a fast second step. Okay? So first step is to add them together, see what the overall reaction is. I'm going to have NO2 plus NO2. Okay? Knowing that, I'm going to go ahead and I'm going to cancel stuff on both sides, just like we've done in the past. And then I'm going to write what I have left. Now, if I said, hey, predict the rate law of this overall reaction, okay? If I asked you to just predict, given just this reaction, and you knew nothing about this two-step mechanism, you would predict that the rate law would be this, okay? Just based on the reactions. Remember that rate laws are reactant dependent only. You could predict this based on the fact that there's only a 1 in front of each thing, okay? This would be your prediction for this overall reaction, but this is wrong, okay? In reality, remember yesterday we talked about how the two-step mechanism, the thing that is the slowest is the thing that's going to have to be used to determine your overall rate law. That first step is the one that's actually the slowest. And that first step then would predict that this is the actual rate law. Since there's two of them, how can I shorten that? Can't I just write NO2 squared? For slow first steps, predicting the rate law is super easy. You just write, using that slow step, what the rate law is based on the reactants only. Okay? The next thing says, if there are any intermediates, indicate them. Yes, ma'am?
So the rate law is always...
Right, so for this particular exercise, in this particular section, pay attention, the rate laws will depend on what the reaction predicts. You don't have experimental data, you don't have data you can plug into an Excel file to try to figure out what the orders are, or anything of that nature. So you have to use the actual reactions you're given to predict your rate laws. Okay? And this is how we do it. So again, for this type of a step mechanism where you have a slow first step, fast second step, that slow first step's reactants are going to be the thing that make it into our rate law. What other questions? Yes, ma'am?
So if there's one reactant, then we just put that one. If there's
Correct.
a million, we just put all of them?
You put all of them, right. Any reactants make it into your rate law.
Okay.
Yes.
And you only look at the slow one?
You only look at the slow one for this type of, so this is the first of the two situations we're going to deal with today. This is the slow first step approach. If your second step is slow, it gets a little more complicated, and we're going to do that next. All right, next thing is to identify intermediates and catalysts. Are there any intermediates? Remembering the definition of an intermediate from yesterday. NO3, it has to be produced and then used to be an intermediate. Are there any catalysts? If you put that for this particular thing, you would not be wrong. Okay? But since it is also a reactant, I would hesitate to say it's a catalyst. Yes?
What's the definition of intermediate?
When it's produced and then used. Yes?
Wait, so how do you know it's
Catalysts
catalyst?
will be very obvious. They're not supposed to be in rate laws. Okay? Catalysts should not be in your rate law. And it should be something you start with and then it gets like used up in the end kind of thing. So they cancel out. Basically, a catalyst is the reverse of an intermediate. Okay? All right, so let's do the next one. Okay, so now questions that I have for you. If I gave you information like what the rate is or what the concentration of NO2 is, could you calculate K? Yeah. You feel good about that? Okay. If I gave you K and the concentration, could you calculate the rate? Yeah. If I gave you the rate in K, could you calculate the concentration? Yeah. Okay. So hopefully you're feeling a little bit better about manipulating rate equations. Okay. Because that is definitely something that will be in our quiz. Yes? Yeah. So this means concentration in usually molarity. Okay. Do another.
One question. What is the overall rate law for the bottom, for the final equation? That's just...
For this one?
Yeah, that's just...
This is this. This is the rate law for this equation.
Okay.
Okay? Does that make sense?
Yes.
This is that situation where you cannot use the overall reaction to determine the rate law. Okay. The next one. Okay, first things first, find the overall reaction. Okay. Boy, oh boy. Yes, ma'am. Yeah, sorry.
Wrong
Just
pronoun.
I'm sorry. It just happened. I should have stopped myself and said yes, ma'am. It's just a reaction for me. Okay. All right. So here's my overall reaction. Do you agree? Do you see how I got there quite yet? Okay. Take your time. You can skip step 2 and start looking for intermediates and catalysts on your own, remembering the definition. Say again? Correct. Yep. I definitely will always simplify like that. Like you saw you had 2 analysts sort of come together. Yeah.
So the left side is all the reactants, the right side is all the products.
Correct. Ooh, you're looking for something that starts on the left and it cancels out on the right after that.
But not an intermediate.
It's the opposite of an intermediate. An intermediate is produced then used. A catalyst is starts and then gets canceled out.
Are we allowed to have more than one?
Absolutely. For sure. Is there a catalyst? There can be more than one intermediate. Absolutely. Yeah.
Explain to me why. Because the two atoms said two and it wasn't produced.
Right and left. In order. Yes.
I thought you had this.
Here's a question. Can you have more than one intermediate?
I thought that had to be one of the products.
Yes, absolutely. Why not?
That's what I was thinking.
Do we have any catalysts?
H2 doesn't show up on the right as a product though.
Yes, it's used up. Catalysts are used up.
They would either be on the same row or they'd be on separate
I don't
steps.
think there is a catalyst.
After, yeah, then it would be or like for instance, you see like that N2O, okay, if N2O was flipped, so it was on if it was like, so if the N2O was on the left first and then on the right later, that's your catalyst. You see that? So if you flip those two. That's a step. Yeah, so if you flip steps 2 and 3, N2O would be a catalyst. I think. Does that make sense? Correct. Correct. Okay, all right, so let's talk. First things first, are there intermediates? Yes, there are.
Why?
There are 2. What are the 2 intermediates?
N2O2 and
N2O2 and N2O. Okay, yes.
What do we look at for the intermediates?
You're looking for, that's a good question. So we were just talking about this. If you're looking for an intermediate, you're looking for something that is produced first and then sometime later gets used up. So you're looking at this like it's being done in order. Okay, look at these reactions like they have to be done in order. So if this is step 1, it would have to be produced in either step 1 or step 2, then it would have to be used in either step 2 or step 3. Okay? If you were looking for a catalyst, you would want to see it in a reactant first, and then later on sometime as a product. So, and I was talking to Ryan about this just now, if you flipped steps 2 and 3, make this step 2, make this step 3, N2O would be a catalyst. Okay, but are there any catalysts at this point?
No.
No catalysts. Okay? So okay, so the intermediate. So let's talk about this. That's okay. So this guy gets produced, right? Then it immediately gets used. So since it's present on both sides, it cancels out, doesn't make it into the overall reaction, which is one of the things that an intermediate has to do. Okay? Same thing for N2O. Produced, then used. Produced, then used. That's an intermediate.
So, and does it have to be in the overall reaction then?
No, an intermediate should not be in the overall reaction. Neither should a catalyst. Those two things are just things that appear in the step processes. They do not appear in the overall reaction. Yes?
So if you do like what you did under step 3, if it crosses out, it can't be an intermediate or a catalyst?
If it crosses out, it's probably an intermediate or a catalyst. Okay? If you're crossing it out, it's an intermediate or a catalyst. Yes?
Okay, so a catalyst has to be in a step 1 reactant, but it doesn't.
No. A catalyst just has to come before it gets canceled out. So it has to be a reactant and then a product. If an intermediate has to be a product then a reactant, a catalyst has to be a reactant then a product. Yes, ma'am?
Like in the same step, or could it be
Different. They can be in the same step or it can be in different steps. Just remember that this is chronological. So if you had, so like I said, if we put this step here, N2O would come first, right? And then N2O would be produced down here. That would make it a catalyst. Yes?
What was the catalyst in this one?
There wasn't one. There's no catalyst here. Good? All right, let's do the hard part. We got the intermediates. We got the overall reaction. You've got it written down, right? Okay, if you had to guess what the rate law was
Do we have to?
from just the overall reaction, what would you predict based on what we talked about? So you would do NO squared, because there's a 2 in front, times H2 squared. This is our prediction, right? This is our prediction based on the fact that if we were just given this reaction, we wouldn't know about this. Okay? So we can't really do this because we know that there's more than one step involved, and we're going to see what the real rate law is by doing a bunch of math. Woo!
There's more math?
There's more math.
Oh, we're not done.
For the assignment,
Oh.
we just have to put a prediction, it just doesn't have to be right.
Say again.
For the assignment, we just have to put the prediction.
No. No. I'm telling you that if you were just going to predict, this is what we'd predict. Now we're going to actually find what the rate law is, and we're going to see how that's different than what the prediction would have been. That's a good question. All right. I don't need step 3, so I am going to just erase it because I need steps 2 and I need step 1. I need the slowest step and anything that comes before it to do this. Okay. First things first. When we did the one before, how did we predict the rate of the slow step? What did we write? Times the concentration of each of the reactants, right? Okay, but here's a red alert. You have an intermediate. You can't have intermediates in your rate laws. They aren't things you can measure, so it doesn't work. Okay? I am going to slightly alter this, and I'm going to write K2. Why? Because this rate law comes from the second reaction. This is where K2 came from. Okay. This is our problem. How we're going to solve our problem involves using the first step, which is reversible. Since this first step is reversible, when we go in the forward direction, we have a rate law constant. When we go in the reverse direction, we have a different rate law constant. Take me at my word here. So this so far you should be able to do. You're just going to see these reactions. You're going to label K2, K1, K negative 1. Okay? All right. If I want to write the rate law of this first reaction in the forward direction, okay, so I'm going to go this way. Where are the reactants? Left or right? Left. These are my reactants, right? What would I write for the rate law of that? NO squared. Do you see that? Why did I write squared? Because there's 2 of them. I could have just written 2NO, but instead I had an NO plus NO. Whatever. We good so far? All right. If I want to write the rate law of the reverse reactions, where are the reactants now? On this side. So I'm going to write this guy. If I go forward, this is my rate law. If I go backward, this is my rate law. Okay. With reversible reactions, one of the things we learned yesterday, the rate of the forward reaction has to equal the rate of the reverse reaction. So this was my forward reaction, right? This was my reverse reaction, right? I just said that these have to be equal. So can I set these equal? I can. My goal is to get an expression that involves reactants that actually exist, so think NO in this case, into this rate law we predicted for the slow step, because that intermediate doesn't exist, right? So we have to put something in there to substitute for that intermediate's concentration that really can be measured. So what are we going to do next? Solve for the intermediate. We're going to solve this algebraic expression to put the intermediate by itself on one side of the fraction. So this one's easy, right? What do I have to do? Divide. Divide by the rate constant. Oops. Okay, we've boiled this down to an equation, right? This is an expression for an unknown, and we have an unknown in this expression, right? So what are we going to do next? We're going to take this whole expression, we're gonna plug it in to my rate law up here. Ta-da! Okay, yes, sir.
So, wait, I think you're ready to get to it.
Okay. Okay. So now I'm going to rewrite this whole thing. This is the rate of the overall reaction, if you will. Because that was my prediction based on the slow step. I'm going to rewrite this. I guess I shouldn't use brackets because brackets mean concentration. Parentheses. NO squared? Well, so now here's the next thing I want to ask you. Yes, I mean, this is the final answer, yes. If you left it like this, you'd be fine. But what happens is, these are all constants, right? A constant times a constant divided by a constant still equals a constant. So they just take this whole expression and they'll just make it a K. So now, look back at what we said. Okay, if we just use the overall, what would we predict? This is different. Our overall reaction predicted H2 would be squared. Not what this is. So when you have a slow second step, you have to do that extra step of solving for whatever intermediate you have and then plugging it back in to get your final expression. If you do not simplify K2 times K1 over K negative 1 to K, that's okay. If you stop at that first one, I'm fine with that. Okay? You stop up there, great. If you recognize that a constant times a constant divided by a constant is still a constant, you can write K. Okay? All right, so those were our first two. Okay, there are some more practice problems. I want you to start them. In this first one on the left, so you're going to see the ones that have the slow first steps, right? So this one, those have slow first steps. That should be really simple, really quick for you. You're going to use that first reaction, that slow first reaction, to predict the rate law. Yes, sir?
Number one of those those 5 things all in one thing, or just 5 separate?
So those are the 2 reactions you add together to get the overall. Does that make sense?
There's 5 though.
Yeah,
Oh, I'm sorry. Okay, so this is, okay. I tried to like save room on my page. This is problem 1.
Okay.
This is problem 2. This is problem 3, these 2 reactions. This is problem 4. So problem 4 has 3, but everything else has 2. So there are 2 of each kind to practice. You can do this.